Without further ado, the title of Brian's presentation today is Advocacy of Conservation Actions for Imperiled Colorado River Fishes in the Grand Canyon of Arizona.
Thank you.
Got it. You can just do one double check with the Zooms to make sure that.
Yeah, is everybody on mute just to?
No, but I know that they can see your.
Oh, can you all see my slides? I know it looks kind of distant. Yes, no. Okay.
Yep.
All right. Thanks, Phaedra, for that. That's Life in Fish Ecology Lab. Phaedra, thank you so much. So today I'm going to be starting off by discussing some challenges to effectively conserving native fishes in altered environments, including within the Grand Canyon, where my study area is located. I'll then go on to discuss the highlights of my 3 dissertation chapters, including the first one, which is a response of native fishes to invasive trout suppression. The second one is an analysis of drivers of translocated fish populations. And the third, I'll be exploring metapopulation scale invasive fish suppression alternatives, and then close by providing some ecological insights and conservation applications that came out of my research. I do want to point out too that this work represents about 13 years of my life and career, and a lot of other people were instrumental in making all this happen. So I'm probably going to be saying we a lot, in other words. All right, first, I'm sure we're all aware that over the last few decades, we've seen global declines in biodiversity, but what may be less evident is that there's the declines in freshwater biodiversity are outpacing those of terrestrial and marine environments. And this is significant because hundreds of millions of people throughout the world rely on freshwaters for their food security and their livelihoods. Freshwaters make up about 1% of our global water supply, but support almost half the diversity of fishes. Invasive species are a significant threat to biodiversity overall. On the right side of my slide here, I've highlighted 4 of the worst invasive, most ecologically damaging invasive species. I'll be addressing 2 of those today in my study. So invasive species are a big threat for native fish, as is habitat alteration. And these 2 factors can interact and synergistically impact native species. So we have conditions created as a result of damming and water diversions that actually creates better habitat for native species. And these both synergistically cause declines in our native fish communities. Inland rivers are important biodiversity hotspots, but they're among the most imperiled freshwater habitats, given the high competition for human water use and the extensive damming and water development infrastructure that's constructed to provide water for humans. That also impacts fishes, including through fragmentation of habitats and blocking of migratory routes. So these stressors are probably no more prevalent in one of our largest rivers in the West, the Colorado River. This river has been coined one of America's most endangered. And it's due to this extensive water development as one factor. There's 15 large main stem dams. Reservoirs behind these dams store about 7 times the mean annual flow of the Colorado River itself. Water managers look at the Colorado River system as this vast series of reservoirs and plumbing infrastructure to provide water for 40 million people. In addition, on top of that, we've introduced non-native sport fish across the entire Colorado River basin, which have significant threats on the native fish fauna through predation and competition. And managers have been struggling for many years trying to control these fish to bolster native fish populations, spending around $2 million a year in Upper Basin, for example. So the primary challenge I'm going to be addressing with my dissertation research and talking to you about today is this challenge of developing, testing, monitoring management strategies to conserve native fishes under these altered conditions. As I mentioned, my study area is within Grand Canyon, which is in the lower basin of the Colorado River. It contains about 280 miles of the Colorado River itself. It's located downstream of Grand Canyon Dam and Lake Powell and upstream of Lake Mead. So within the Colorado River system, there's a high degree of endemism. About 3/4 of the main stem large river fishes are found nowhere else in the world. However, about half of these are listed under the Endangered Species Act. And within Grand Canyon, 3 of these species have been locally extirpated. So much of our conservation work has been focused on the previously endangered humpback chub, now threatened, and the other native suckers in the river system. So these Colorado River fishes evolve in disturbance-prone environments with seasonally warm thermal regimes and lots of flow variability. This upper plot here, I have an example of hydrographs showing several different wet water years in a tributary in Grand Canyon, where you have this somewhat reliable spring runoff with summers punctuated by these really intense, short duration monsoon floods. There's another example on the bottom of Havasu Creek at flood stage. So in order to thrive in these habitats, the native fish community developed unique life history strategies, including longevity. Many of these fishes live up to 40 years old. They're highly fecund, they're migratory, and they have unique morphology, and all of these attributes allow them to have good recruitment years when conditions are ideal, which is somewhat rare. So Glen Canyon Dam was constructed on the Colorado River upstream of Grand Canyon in 1963, and it had profound impacts on the hydrologic regimes. This is a great figure I found recently showing just over 100 years of flow in the Colorado River at Lee's Ferry. And you can see when the dam was constructed, we lost this high spring runoff, and we lost these monsoon floods that would have been fairly common in the Colorado River. We now have a more stable flow regime. I do want to highlight, however, if you notice these small blips in the hydrograph in a few years, those are high flow experiments meant to restore some of the ecological values within Grand Canyon National Park. Glen Canyon Dams also altered the thermal regime within the park. Here I have the water temperature measured continuously at Lee's Ferry after dam closure, and you can see temperatures decline and stayed more stable. However, more recently, as reservoirs declined, I have the Lake Powell elevation here in the lower plot, you can see that we were getting some warmer temperatures that are approaching the minimum spawning temperature for humpback chub. So both of these factors limited humpback chub and native fish reproduction within the Colorado River. So the stable and more predictable habitats that were the result of damming now favors fishes that are involved in these more stable and predictable environments, including salmonids, the trout, that have been introduced in the tailwaters, the tailwater in Grand Canyon for a sport fishery. So brown and rainbow trout are one of the most widely introduced vertebrate species in the entire world. Their introductions have been both inadvertent and purposeful. They thrive in these altered habitats. They're great sport fish. However, they have significant impacts to native fish fauna due to predation and competition. Here I've just highlighted the ranges of both of these species. In the lower figure here, you can see the native range of rainbow trout hatch, and the red solid color is where they've been introduced. And also for brown trout, native to Europe and Western Asia, North Africa, and introduced in all these red hatched areas. So you see both of these species having a tremendous impact on natives throughout the world where they've been introduced. Nonetheless, despite all these impacts in Grand Canyon, we've had a native fish community sustained by spawning and reproduction in tributaries, including the Little Colorado River here. And in fact, more recently, native fishes have come to dominate the fish community in Grand Canyon, which is really a gem in the Colorado River system and rare. So how do we continue to conserve these riverine fishes? That is the general theme of my presentation today. So we can restore habitat. We can start through high flow experiments or other designer flows meant to restore habitats or improve ecological values. However, the outcomes of these experiments can be difficult to predict. For example, we found recently that high flow experiments in the fall are stimulating brown trout movements and colonization of the Lee's Ferry reach. They also can be quite expensive, into the millions of dollars. As an example here, I've shown a flow pattern for a Glen Canyon Dam high flow experiment, preceded and followed by peaking for hydropower generation. So you can see the short duration event here in the middle. Alternatively, we can directly manipulate and manage populations of fishes, either through hatchery propagation and stocking, translocations or reintroductions, or suppression of invasive species like the brown trout here. But again, outcomes of these operations are also sometimes uncertain. Oftentimes, management agencies have minimal resources to conduct long-term monitoring, or they might lack clear objectives for their projects. So the primary goal of my dissertation research was to evaluate the efficacy of these actions in restoring and maintaining native fishes. Okay, moving into chapter 1. For chapter 1, I evaluated the responses of native and non-native fishes to invasive trout suppression in Bright Angel Creek. Here's the location of the study reach, Bright Angel Creek. This stream has been the primary source of reproduction for brown trout for many decades. It also, for the entire Grand Canyon, you can see here in this upper plot, I have the catch rates by river mile plotted, and you can see the highest densities in the Colorado River just adjacent to the Bright Angel Creek. Bright Angel fish community, there's records of 6 native species in and near Bright Angel itself. You can see these fishermen here, this photo is taken in the 1910, 15 range. This is a stringer full of humpback chub this photo was taken just outside of Bright Angel Creek itself. But as the 2 salmonids were introduced into that stream, they replaced the native fish fauna. And at the beginning of our study, there was mostly speckled bass and bluehead suckers remaining, with flannelmouth sucker only being observed on spawning runs during the spring, and no evidence of rearing was found. So for this analysis, I used 3 past depletion electrofishing samples collected between 2010 and 2018. This was the 3 past depletion conducted throughout Bright Angel Creek in these 5 reaches. So the sites were nested within these reaches. We also had a weir installed near the mouth to intercept brown and rainbow trout in their spawning migrations out of the creek. So at the beginning of this study, we assumed that brown and rainbow trout were having a really strong negative impact on the native fish community and driving down net populations and limiting their distribution. Nonetheless, over time, at the beginning, we thought we could, through suppression of trout, we could get lower abundances of trout, which would then allow for increases in the distribution and abundance of native fishes. But nonetheless, we were unsure how the native and non-native fish might respond to both the trout, or both the electrofishing, as well as environmental variation due to changes in temperature or flooding. So my primary research objectives were to quantify the temporal trends in abundance with streamwide trout suppression in both native and non-native fish, and assess the importance of temperature, flow, and trout as drivers of native fish distribution and abundance throughout Bright Angel Creek itself. So to quantify the temporal trends, I used depletion models to estimate abundance or the total catch of the native suckers, and assess drivers of the distribution of and abundance of native fishes. I used generalized linear mixed effects models with trout density, monsoon and spring flooding indices, and thermal variation as covariates, and I selected the top model using AIC. I wanted to point out that there's both seasonal and longitudinal thermal variation in Bright Angel Creek itself. So closer to the headwater spring source, we have muted seasonal variation in colder temperatures. And in contrast, near the mouth, there's much more variation in temperature, and the thermal regime is warmer in general in the summer. And so for this analysis, I used a variable of distance of each site from the Colorado River as a proxy for temperature. Also, there was quite a bit of variation in flow across the water years in Bright Angel Creek. Here I've highlighted 2 very different water years. You can see in 2012, there's a very limited spring runoff, but we had a really large one in 2017. So I captured this seasonal and annual flow variability using 12 flow metrics. But many of these were correlated, and so in order to simplify the analysis and reduce the number of variables, I used a principal components analysis where I developed synthetic variables representing a gradient of spring flooding intensity. And on PC2, there's a gradient of weak monsoons to strong monsoons. So each one of these variables were included in my models as covariates. So between 2010 and 2018, I used data from 877 3-pass depletion samples collected throughout the creek. We removed 42,830 brown trout and 7,856 rainbow trout. And over that time, we observed a trend in rainbow trout of decline in rainbow trout of 80% and a 91% decline in brown trout. So these stacked bar charts are the abundance by reach over time for each one of the species. In contrast, there's a 480% increase in native fishes throughout Bright Angel Creek. Most of that increase occurred in the lower reaches 1 and 2, and a little bit in reach 3. And interestingly, we can see, as I mentioned earlier, there's no flannelmouth suckers rearing in the creek until we reduced trout to a fairly low level. And then when trout were at their lowest levels, we saw this huge increase in recruitment of flannelmouth suckers in the creek. So the top model to predict the distribution and abundance of native fishes, I use native fishes aggregated in this case, included spatial thermal variation, the trout density, spring flooding, and monsoon flooding indices. And here in these plots, and the two in the following slide, I have the covariate on the x-axis, native fish abundance on the y. So in this first plot here, you see there's very few native fish as you get into the colder and upper reaches. However, the colors indicate the different years of the analysis. And you can see this pink, which is the latest year, native fish have increased their distribution upstream towards the headwaters that are cooler. And that occurred as trout density declined. Again, you can see very few native fish at higher trout densities. And in addition to that, we saw a high abundance of native fishes following years with high spring flood magnitude, and also during years with very weak monsoons. So limited flooding during the summer. So in summary, mechanical suppression was effective. We saw 480% increase in native fishes. By about the time trout had declined by about 60% or more. And incidentally, the brown trout catch in Grand Canyon, adjacent to Bright Angel Creek and Colorado River, was at a 20-year low and continues to be, suggesting that suppressing a source of an invasive species has impacts that extend beyond the area where you're applying your management. And also, again, we found native fishes in the highest abundance in warmer sites with fewer trout and during years with high spring flows and weak monsoons. I wanted to point out that this type of response in native fish to a trout control project or any sort of non-native fish control project is rare, and this is a really remarkable increase that you don't often see with these high investment trout or non-native fish suppression alternatives. One second. It's a lot of words. Sorry. Okay. All right. For chapter 2, I assessed the drivers of translocated humpback chub populations. Excuse me. Humpback chub population dynamics in 2 tributaries in Grand Canyon. To provide a little background to start with, translocations were initiated early on to enhance juvenile recruitment because it was limited in the main stem by trout and colder temperatures. And also, it was at a time when humpback chub were only reproducing in the Little Colorado River. So it was an attempt to enhance the redundancy of the species in other areas in Grand Canyon. So beginning in 2009, we started translocating 1,102 fish from the Little Colorado River to Shingle Creek. And in 2011, we initiated translocations to Havasu Creek of 1,956 fish. These translocations generally occurred in batches of 200 or 300 fish per year, but with the exception of in 2014, we released about 500 fish in Havasu Creek. Some initial outcomes of these translocations included that we reserved and documented reproduction after just 2 years in Havasu Creek. However, in contrast, while growth and survival of humpback chub in Shinnecock Creek was fairly comparable to the source population in the Little Colorado River, the population, as well as bluehead suckers, were extirpated by a fire that was followed by an ash-laden flood event. Other questions remain whether these fish were simply flushed out of the stream or whether they suffered higher mortality rates as a result of the ash and flood. So in both of these translocation sites, we saw populations of humpback chub and other fish species fluctuate, of course. Some of that was due to translocations, but we, excuse me. Okay. But managers are often concerned with the state or abundance of a fish population at a given point in time and snapshots into the future. But these snapshots don't often give us a clear picture about what's driving the change in the populations, either negative or positive. And once managers can understand what's driving those population changes, they can understand the limiting factors and develop management strategies to try to address them and conserve that native fish population. So we know that adult survival and juvenile recruitment into the adult stage drives population growth, as does somatic body growth. That growth influences both survival and recruitment rates. There are many different drivers that affect both of these demographic rates, including competition or predation with rainbow trout, intraspecific density dependence, variations in temperature, changes in the food base, also variation in drought and flood events. And also, to understand what was driving the population growth in the translocation sites, I also wanted to account for fidelity and dispersal out of the creek into the Mason Colorado River. So this is the main goal of this chapter, is to understand the drivers of the survival, recruitment, and somatic growth in translocated populations. I wanted to point out there are important differences in the translocation sites and the source stream. This is Shinnecock Creek on the left and Havasu Creek on the right. They're very different in temperature, flow, and physical habitat. And definitely much smaller and different than what's considered typical main stem Colorado River fish habitat in these much larger systems like the Little Colorado River or the Colorado River. And also, it was important to note that translocation sites were chosen upstream of barriers to the Colorado River. So the idea was, this is intentional, to prevent other invasive species from moving into translocation sites and impacting those translocated populations. However, in the Colorado River, there's brown trout, there's catfish, and there's other highly piscivorous species there. However, the fish communities in those receiving streams differ also. Rainbow trout are relatively rare in Havasu Creek, but they're actually quite abundant in Shinnecock. And at the time, managers thought that rainbow trout were less of an impact or less of a threat to humpback chub and weren't as concerned. But nonetheless, we did implement some suppression to remove trout from those sites. I'm going to quickly go through the logistics of translocations. So humpback chub were collected during the juvenile or larval stage from the Little Colorado River. They're flown out of the stream, driven to a hatchery where they spent 8 to 12 months rearing. During that time, they were given parasite and disease treatment. They're given flow training. And once they're large enough, they're pit tagged. In case people don't know, pit tag is like a unique identifier that's injected into the fish, similar to a chip in a pet. They're weighed and measured and then driven back to the park and flown into release sites via helicopter and set free. For this analysis, I had a complex and vast amount of data, and I'm not going to go into it all in detail, but wanted to point out that I used encounters from translocations to populate my market capture models, as well as sampling that was conducted within translocation sites twice per year using hoop nets. But this is a schedule of my data collection, by the way, over time. I also was able to take advantage of a vast amount of data collected by multiple agencies in the Colorado River through the Glen Canyon Dam Adaptive Management Program. So that included Colorado River monitoring, Little Colorado River monitoring, And then 3 mostly continuously recording pit tag antennas. These fish dispersed from the translocation sites and then were picked up later by these other monitoring programs. I also used temperature and flow variables and covariates to develop covariates for my marker capture models. So for somatic growth, I used linear mixed effects models with flood pulse frequency and counts of trout and humpback chub as covariates. And for recruitment, which I defined as newly tagged humpback chub that were entering the population at about 150 to 200 millimeters when they also mature, I used a temporal symmetry model for that analysis with covariates of natal year trout and chub, and as well as flood pulse frequency during the natal year, so the first year of life. And for survival, I used the Barker model with covariates on both survival and site fidelity. And similar to chapter 1, I used a principal components analysis to simplify the analysis for survival. In this case, for Havasu, PC1 was a gradient of temperature and flood intensity, or flood intensity and frequency. And PC2 represented a gradient of more trout and more humpback chub, including the number of fish that we translocated. So the top models for growth in Shinmu and Havasu Creek explain between 67 and 84% variation in growth rates in those 2 streams. Flood pulse frequency is an important driver of growth rates in both Havasu and Shinmu Creek, and it varied across seasons. So on the x-axis here, I have the driver of the covariate, and the y-axis is growth rate. And you can see that at higher flood pulse frequency, growth was higher in both streams in the summer, but it declined with more floods in the winter. I also found a negative relationship between humpback chub catch rates and growth in Havasu Creek. And I found a negative relationship between rainbow trout catch and growth rates in Shinmu, which vary between seasons with a steeper decline or stronger effect in the summer. Moving on to recruitment. Top model for recruitment included a negative relationship with rainbow trout abundance and humpback chub abundance. And I did find support in the modeling for a relatively weak effect of flood pulse frequency, suggesting that some of those fish could have been blown out of the stream as juveniles during strong monsoon seasons. On the right here, I have the recruitment rates estimated over time. You can see they're fairly variable, with the strongest recruitments or large year classes in the last couple of years of the study. And on the lower graph here, I have the population growth rate, or lambda, which was generally stable or positive. And you can see that it generally matches fairly closely the pattern in recruitment, suggesting that this modeling suggests that population growth was primarily driven by juvenile recruitment. I found a group effect for survival in Havasu Creek. Groups consisted of non-translocated and translocated fish. I wanted to see if there's a difference in survival between those 2 groups. I also found a negative relationship with humpback chub density and growth. And I found a positive relationship with flooding and temperature. This plot here shows those monthly survival rates for both groups over time, with the stable, or the top model included a constant survival for the non-translocated fish that were born in the site, but it was lower. And you can see that the intervals with the lowest survival rate actually corresponded to the times when we put the largest number of fish in the creek, which was that batch of 500 in 2014. In Shinmu Creek, there are unfortunately no covariates in the top model. However, although we saw fairly high survival relative to the LCR, which is represented by this dashed line here, we did see a pretty big drop in survival corresponding to the interval of that large fire and flood event, suggesting those fish did suffer high mortality rates during that time. So in summary, I found density interspecific density dependence in survival, growth, and recruitment, suggesting that managers need to very carefully consider the carrying capacity of a reintroduction of translocation site prior to putting fish in there. And maybe less surprising is that I found a negative relationship between rainbow trout growth and recruitment, and humpback chub growth and recruitment, suggesting that ideally you should eradicate or suppress the invasive species present in your site before conducting a translocation or reintroduction. And finally, I found that post-fire flooding reduces survival of humpback chub. I wanted to point out that it's fairly well documented that flooding in rivers with broad, large floodplains provides benefits to native fish, through increased access to resource, either food or space. But it's less well documented for canyon-bound reaches like Havasu Creek here on the right. However, my results do support findings of Baxter and Bain that found that native fish, including humpback chub and Little Colorado River, had increased feeding opportunities and higher gut fullness during periods of the summers when there was more flooding. And finally, translocation was successful. This is another rare occurrence. Translocations for endangered fishes especially often fail. Fish don't establish or they suffer high mortality rates. In this case, even if the fish were extricated from Shinmu, there's still lots of adults kicking around in the main stem. So anyway, success. Okay, and now on to my final dissertation chapter, which is an exploration of metapopulation scale suppression for brown trout established in the Colorado River system below Glen Canyon Dam. So this chapter differs from my first chapter in that I'm not just focusing on one tributary, which is Right Angel Creek. In this case, I'm focusing on the entire system that's interconnected through dispersal between reproductive areas. So I simulated 4 subpopulations within the metapopulation, including below Glen Canyon Dam, population of brown trout that's recently expanded and established itself there, and then 3 subpopulations within upper, middle, and lower Bright Angel Creek. And this conceptual model here shows the relative carrying capacity or population size for each one of these subpopulations, the distance between them, and also the colors indicate gradients of temperature, with the reddish or pink being warmer, and the dark blue being the coldest. Also, I wanted to point out that there is a waterfall barrier between the middle and upper Bright Angel Creek subpopulations, preventing immigration upstream. So my objectives were, through the use of a population viability analysis, compare suppression scenarios that evaluate the effectiveness of different suppression approaches across different life stages and across different subpopulations. And I also wanted to compare future reservoir storage and climate change alternatives with and without suppression applied. I wanted to point out also that this approach is somewhat unique. Often PBAs are used for analyzing conservation action alternatives for imperiled species, and fairly rarely implemented for invasive species, and especially in a metapopulation like this. So I used a dynamic habitat disturbance and ecological resilience model for my simulations. This model is advantageous is that I could model population dynamics within an individual subpopulation, which were these yellow circles here, while also simulating habitat changes that might differ between the subpopulations. And also I could simulate dispersal rates between them. My modeling approaches had advantages in that there's a broad literature out there describing brown trout vital rates and demographic rates. However, I also had empirical data from within the study area that I could use to parameterize the model, including survival that was calculated from market capture data in the Lee's Ferry Reach or Colorado River. I did some egg counts a few years ago, which I used to estimate reproductive rates. And finally, we took advantage of a 20-year market capture data set for brown trout throughout the Colorado River to estimate dispersal and movement probabilities between the subpopulations. I simulated 4 different life stages, including age zeros, juveniles, small adults, and large adults. And this was advantageous is that I could apply different harvest approaches across these different life stages. So for example, fishing gear types selectively can catch and remove different stages or sizes of fish in some cases, like electric fishing, where larger fish are usually more susceptible. My suppression scenarios differed a little bit between the Bright Angel Creek subpopulations and the Colorado River. I used electrofishing in the weir, just how I described it in chapter 1. I also simulated the use of a chemical pesticide to eradicate trout from the upper section of Bright Angel Creek above that waterfall. I used boat electrofishing in the Colorado River and simulated results of an incentivized harvest program that's ongoing, where the Park Service is paying anglers to catch and remove brown trout. It's going to be a lucrative business for some people. And finally, I simulated a red and egg disruption that could be conducted using mechanical means or through the use of the dam. I combined these scenarios, or these approaches for my scenarios. I also wanted to simulate climate, the future climate. And as part of this research, I found that spring runoff is important for brown trout reproduction, and yet it's expected to decline in the future along with increasing air temperatures. So I was able to obtain some data from the NPS Climate Change Response Program. They're showing historic runoff and future runoff from 12 different climate models. I selected 2, a wet and a dry scenario, which are easier to say that way, but they're more like a dry and less dry scenario. To simulate future climate change, this is essentially spring runoff over time with the next 80 years. I use these data and apply them to habitat suitability functions within the model to simulate changes in habitat for H0 survival. I also wanted to simulate different reservoir storage scenarios that are going to have a profound impact on the temperature downstream of Glen Canyon Dam. So I used data from Jack Schmidt's Center for Colorado River Studies reports to estimate or to simulate changes in temperature over time for 3 different plausible reservoir storage scenarios. The first one is where managers might decide to store more reservoir or prioritize storage of water in Lake Mead versus Lake Powell upstream. This resulted in some of the warmest temperatures. Or a status quo scenario where we expect both reservoirs to decline, which is currently occurring due to climate change, drought, and water use. That's sort of a moderate increase in temperature. And finally, one where we choose to prioritize water storage in Lake Powell upstream of the Grand Canyon, which would result in the coldest temperatures. So in summary, I had 6 total climate scenarios with these 3 combined with the 2 from Bright Angel. I measured outcomes of these simulations with the minimum population abundance, or metapopulation, so the entire population across the entire system. I also used the time to quasi-extinction to compare and contrast scenarios, which was defined as abundance less than 5% of the carrying capacity. Okay, there's a lot to unpack here. I'm just going to point out a few different highlights, but this plot shows the minimum metapopulation abundance for all of the different scenarios that I ran. The yellow boxes are where I applied suppression only to the Colorado River subpopulation. The light blue is where I applied it to only Bright Angel Creek. The dark blue and these red diamonds is where I applied suppression across the entire metapopulation, and the red is with climate change. And these red squares are only climate change with no suppression. So the highlights are that to be the most effective in the Colorado River population itself, you need to apply both mechanical removal, electrofishing, combined with some other technique to target all the different life stages to be most effective. In contrast, the 2 least effective when the suppression is only applied to the Colorado River includes the current level of incentivized harvest, which is from NPS data on the website, and red disruption. And both of these do not target all the life stages. One of them doesn't target H0s, and red disruption only impacts eggs and reds. In contrast, when we apply it only to Bright Angel Creek, even at the extensive rate that we have, we don't get very far towards metapopulation quasi-extinction. Interestingly, the least effective is this one where we have the weir installed, and that is because the weir blocks immigration into the creek and creates more dispersal towards the Colorado River population, which is consistent with the smart recapture study that we found, where fall high flow experiments in the weir initiate more removal upstream away from Bright Angel Creek. Contrast to both of those, the most effective are when we apply it, obviously, across the entire metapopulation, with the exception of two. So under climate change, this is multiple tools that we're currently applying, and here's current suppression for without climate change, and those are the least effective, suggesting that we need to do something different there. So this is a trend. These are trends in abundance over time for 4 examples. I'm just going to highlight 2 of them. Excuse me. So when we apply all the different tools that we have available across the entire population, we can reach quasi-extinction in 8 to 9 years, potentially, in the entire system. In contrast, under our current suppression, we never quite reach quasi-extinction over the 30-year duration of my simulations. And finally, here are the subpopulation abundances over time for the climate change scenarios without suppression. A couple of key points I wanted to highlight here are that without any suppression, the only scenario that drove the population towards quasi-extinction was the fill need first dry scenario. That's this one here. Quickly declined the population, or initiated quick, rapid declines in the population, concurrent with high rates of dispersal into the lower and middle Bright Angel Creek subpopulations. So what also is important here is that we see that Bright Angel Creek will act as a refuge into the future, because there should be suitable habitat in the middle and upper reaches, at least into the next 30 years under the scenarios that I simulated. So quick point I wanted to make here is that disrupting that connectivity between the Colorado River and Bright Angel Creek could have a really big impact on the future populations in those streams and potentially prevent Bright Angel from becoming a refuge and maintaining a large population of brown trout. Here's just, with the weir installed, it's a very simple, low-cost alternative, could be highly effective in the future. And finally, in summary, I found that metapopulation-wide suppression of multiple life stages is necessary to effectively decline in the brown trout population and protect native fish. Connectivity leads to metapopulation resilience, consistent with metapopulation theory, and also the rate of the decline in the metapopulation system-wide heavily depends on water storage decisions, and Bright Angel Creek will serve as a refuge in the future. There is hope. I've demonstrated that when we can potentially use our resources effectively and efficiently to cause a pretty significant decline in Bright Angel, or in the brown trout, and protect our native fishes. In conclusions, I found that I wanted to go over a few of the conservations of my research to both conservation and ecology. I found that I demonstrated that suppression of invasive species can benefit native fish communities. I also gained insights from detailed analysis and long-term monitoring of both suppression and translocations to provide information on humpback chub and non-native fish population dynamics, but I wanted to point out that multiple years of monitoring is necessary to drive any sort of conclusions. Metapopulation scale invasive species management is also necessary, of course. I found that native fishes thrive in dynamic environments in Grand Canyon, where spring flooding was an important aspect of native fish reproduction, and it might also limit brown trout recruitment and reproduction, which is consistent with the literature for brown trout. I also found that increased fish growth, native fish growth and survival increased with flooding in my canyon-bound systems. And finally, the establishment of a metapopulation of invasive species leads to persistence and resilience to habitat degradation, also consistent with metapopulation theory. And a rapid response to this type of expansion could prevent metapopulation establishment and lead to more effective suppression in the future. I wanted to thank my amazing committee. I couldn't have had a better, more supportive committee through my PhD program. So Dr. Phaedra Booty, Mary Connor, Mark McKinstry, Jack Schmidt, and Charles Kulik with his whimsical bird hat on. I really appreciate all of your support and mentoring through my program. My work was funded and supported by the Bureau of Reclamation. I want to thank Mark for facilitating that, and also by Jack Schmidt, Center for the Colorado River Studies. Thank you so much for supporting me. I also received support from the USGS Utah Cooperative Fish and Wildlife Unit, Utah State's Ecology Center, and the Department of Watershed Sciences. And I also received an Albright Worth grant from the National Park Service. Logistics support was provided by Reclamation, Grand Canyon Conservancy, Johnson Foundation, the Park Service, and also the Havasupai and Navajo tribes provided us access and logistical support to conduct translocations. And I wanted to thank my wife Susie and my family for supporting me through this. It's been tough at times. And I received support from many different people while conducting this work, and primarily from my team at the Park Service. Amanda Smith, Bob Shelley, Rebecca Kohler, and Sarah Haas, my supervisor. Thank you. And I guess I'll take questions if anyone has them.
Might tell the people who are on Zoom to put their question in the chat or raise their hand because you'll have to unmute them.
Okay.
To use them.
Yeah, if any, I don't know if anybody heard that, but if you have questions for me, you can chat. Okay, I see a couple. The first, you can't see this. No.
No, we can't. It's up on the screen.
Okay, so the first one is fallen sucker population in Mason is rising. At the same time, it started going back into Bright Angel. Did you look at determining if it was the reason for the increase in Bright Angel or just brown trout suppression? So the primary increase in flannel suckers within Bright Angel Creek itself came from large numbers of juvenile fish. So it's recruitment in the creek itself. And I have a model of just flannel suckers, and the main driver is brown trout abundance. But I didn't show that due to time constraints. And the next one is, given that the warm water is bad for brown trout but good for centrarchids coming through Glen Canyon Dam, which would be better to manage for brown trout or centrarchids? Or centrarchids coming up from Lake Mead? Yeah, so we're wrestling with the idea of as reservoirs, the powell is dropping, seeing fish coming through the dam as that warmer layer of the reservoir that's more hospitable to native fish is closer to the intakes. So I think what I envision for this future that's horrifying in my brain is that we have a situation where brown trout are still doing okay, and there's an overlap in the suitable temperature regime between smallmouth bass and brown trout where we have both. And seeing what smallmouth bass have done in the upper basin, like wiping out humpback chub from Yampa, I'm more terrified of them than brown trout. Lots of good jobs. Anybody have any questions? Tim?
Great talk. I really enjoyed that third chapter in particular. Have you considered extending that to look at the relative costs of those different suppression methods? Like how much would your control budget need to increase to hit any of those strategies that actually met the quasi-extinction? And maybe what other management actions could you drop in order to make up that budget difference?
Yeah, that's a great question. So I didn't actually do a cost benefit analysis, but I think that would be a really important next step. Mechanical removal is a really labor intensive, expensive operation in a giant way, and especially in the Colorado River. And the capture probabilities that I simulated here are lower than what you'd expect in Bright Angel, where we get 50 to 80% of the trout, So that would be a really important thing to do in the future. Yeah. Casey.
So I have a question about your third chapter as well. Your model results So you split Bright Angel Creek up into 3 reaches that may or may not be true separate populations because they seem close together. I understand for the upper reach, it's probably because that waterfall barrier separates that population, but your responses for the lower and the middle reach were pretty similar. You think that you could come up with a more parsimonious model by just combining them, or did you have a rationale for splitting those lower reaches?
The thermal regimes are pretty different, and I think I took the slide out that I have them plotted. That was the reasoning for splitting them up that way. I wanted to represent kind of a middle, kind of an optimum temperature range, and lower, which is warmer at times. So yeah.
Your first chapter, 2017, was kind of the only big spring runoff year. And that came out in your model as being important. You know, with just 1 year like that, how much do you think you can separate the effects of, you know, all the removal? Just seems like there could be a confounding there.
Yeah.
And especially when you were talking about in the third chapter, how spring flooding could be beneficial for brown trout and so on.
Yeah, I might have misspoke on that. So, hold on. Wait, I think I actually have a slide. Why is that right there? Hold on. So this is the relationship between spring discharge and brown trout H0 abundance. So there's kind of a peak optimum, and then it's very limited at high spring runoff. But getting back to your main question, yeah, I thought this might come up because there is one really good spring runoff year, and the rest of it's fairly low. I think I discussed that limitation in the paper, but also the I kind of try to count for all the different variation and potential drivers of abundance in those sites. And I think it's real, and I think that pattern's held since the years since. So we've had a couple of nice runoff years, like in 2019 was a good one. And then the last 2 years, runoff has been abysmal, sorry. And brown trout exploded, unfortunately, and the native fish have had no recruitment. Mainly 0. So, but yeah, it's a good question.
Yeah, I have a follow-up question. I have 2 questions, but I'll follow up with that one first.
Sure.
So from what you just said and the results, especially from chapter 1, good spring runoff is important and monsoons are bad, but climate change is saying more dismal spring runoff and more big monsoon events. So what do you recommend? How do you counter
Reduce
this?
emissions. Yeah, that's a great question. Yeah, I haven't gotten that far into it. We the climate change response program is doing a big analysis for us, and I just got the draft of it a couple weeks ago, and I plan to do some more work looking at those types of questions in the future. But yeah, it's a great question. I mean, those things are out of our control in Grand Canyon, obviously, because these streams had fairly natural runoff regimes. They're driven by springs. Yeah, it's going to be a real challenge in the future for sure. I think the main thing would be to prioritize your management efforts in places like Havasu Creek, which probably are going to have less of that. I mean, monsoons might be there, but there's really limited spring runoff anyway, and we still get reproduction there. Yeah, it's tough. Thanks. Yeah,
My other question was more about chapter 2 with translocations. A lot of fish studies look at individual characteristics that make, personality, genetics, whatever it may be. Are you doing any of that, or were you able to incorporate that in your models?
No, it's not in the analysis. We do have there is some analysis of the genetics of the fish there. I saw an email the other day. I think the analysis is done. I haven't seen it yet, but that's about the extent of it. And that's more to just maintain genetic integrity of the site, where we might want to interject some new fish into the population. And that's in our the Park Service's comprehensive fish management plan, like when it should be augmented.
Great job.
Great talk. That was really interesting. So this is probably an easy question, but so a lot of your work was like recruitment in the tributaries, but what happens when the fish get up to the main stem? Is the idea that high recruitment in the tributaries means large survival rates in the main stem? Like, is there a correlation between the two, or what's the focus on the tributaries?
Yeah.
So much.
So I don't know if I went over this, I think I meant to, but the recent temperature increases there's been evidence of production in the main stem. I haven't linked, I have done a little bit of analysis actually. The translocations themselves have bolstered the main stem populations, at least around Shinnemoo. I haven't done it for Havasu yet. But unfortunately, the fish that we tag in Havasu, I tried to, they're very rarely recaptured in the main stem, so I'm not really sure how, I mean, assuming that the fish are flushed out and they're recruiting to the main stem population that's been growing downstream of Havasu, but we haven't made a direct link yet to the tributary necessarily. Yeah.
You might just comment a little bit more about why you might start in the tributaries with your management activities too. I mean, it's a lot more in your control,
Yeah,
right?
right, yeah. I think, I mean, it's easier than reoperating the dam, I think, right? You know, Mark? There's smaller habitats. I mean, the brown trout part of it, that was their spawning source. I mean, we've sampled all the other tributaries and there's main stem monitoring going on, and they're pretty rare in the main stem, and other tributaries just a couple here and there. So that was the reason for Bright Angel. We initially started suppressing trout there at a really small scale and quickly realized that unless we do the whole creek, we're not going to get anywhere. In the translocations, again, those were primarily to create new protected populations of chub.
Got a few questions in the chat you might want to address. You have one from Dave Spees.
Oh,
Try not to ignore the
thanks.
Zooms.
Okay, hold on. I gotta. Oh, wait. Okay, hold on.
Maybe just a couple.
Yeah, okay. So finish. Okay. I might have missed this, but did you simulate mechanical removal of brown trout in this area in one of your metapopulation scenarios in chapter 3, or were the removal scenarios? Oh, yeah, Kim, I had a mechanical removal suppression simulated in chapter 3 for release start 2 using Charles and Kulik's capture probability estimates. Hunt registry and incentivized harvest and volunteer hunts to control non-invasive species based on the results, specifically looking at the need to control metapopulations. Do you think these techniques are likely effective? What would be required to make those techniques work effectively? That's a great question. So yes, when I was writing this paper towards the end of it, it's getting close to being submitted. I did a literature review and I didn't find a whole lot of examples or any of incentivized harvest that was the only tool. I found one, I think it was in Idaho in the lake, where they had incentivized harvest as part of it, a larger control program. It also focused on gill netting and I think another approach. So I think that to make this effective, I think incentivized harvest could be a good thing if we could increase the harvest rate by 5 or 6 times, but it also needs to be, you're not impacting the H0s, which I also found in that paper to be the life stage that the population was most sensitive to harvesting. It's more data I didn't show. So it needs to have those 2 components, I think.
I think we better wrap up. Maybe we can capture the chat and you can respond
I can
to
yeah.
people later. Let's thank Brian again and we'll go on to the rest of the defense.